PDF of a vector review on D2L in the course material section, and I'll assign that as something to read too. But I'm just going to give you sort of the highlights of that today. Okay, so first of all, the way that I'm going to write vectors is as a column matrix. So A, B, C like this is the equivalent of AI plus BJ plus CK. Okay, and I'm going to do that. It's useful in a lot of ways. There are a lot of matrix calculations that you can do with vectors. And in order to do those matrix calculations, you have to treat them as a column matrix like that. So I'm going to take advantage of that. In 2D, so if I write AB like this, that's the equivalent of AI plus BJ. And as far as doing cross products and stuff, you can think of that as the equivalent of AB0, just like you can think of it as AI plus BJ plus 0K. So the first thing we have to talk about is expressing vectors as components. And in math, there's really no reason to think about different orientations of coordinate systems. It's you can always just orient the coordinate system however you want. In engineering and physics, coordinate systems stand for something physical. And so sometimes it is important to think about how a certain vector is expressed in one coordinate system versus another one. So let's say that we start out with this vector. Let's say it makes an angle of 30 degrees with the horizontal, and it has a length of 1.5. And we want to know what the components are. It's important to remember that before you can write vector components, you have to choose what the coordinate system is. So first, you must choose a coordinate system. In math classes, the coordinate system is pretty much always x-axis horizontal, y-axis up, but that doesn't have to be the case. And so you have to be clear to yourself about what coordinate system you are using. So let's do it two ways. So first, let's say that our coordinate system is like this, where the x-axis makes a 30-degree angle with the horizontal. And then second, in the coordinate system that we're used to, where x is horizontal and y is vertical. Well, in the first case, you have a coordinate system like this. The vector is oriented exactly along the x-axis. And so the coordinates are just 1.5 in the positive x direction, 0 in the y direction. In the second case, let me try to make that look parallel. That's a little better. Okay, so length of 1.5. This angle is 30 degrees. And so the components for that one are 1.5 times cosine of 30, 1.5 times sine of 30. And that is 1.299.75. Okay, so the components of a vector depend on the choice of coordinate system. New coordinate system means new components. Once you have a vector expressed in components, so now we're going to talk about some calculations to do with vector components. So first, adding two vectors. And I forgot to mention, does anybody have a TI calculator other than Texas Instruments? Does everybody have TI calculators, graphing calculators? Okay, so I'm going to try to bring up as we go how to do vector calculations in different TI calculators. If the calculator you have works a different way, bring it to office hours or something, and I'm sure we can figure out how to deal with it. Okay. So I'll talk about how to enter vectors here in a second. But so adding two vectors. So let's say that you have a vector A, B, C, and you're adding it to a vector D, E, F. The sum of those two vectors is an x component of A plus D, a y component of B plus E, and a z component of C plus F. And I think every TI calculator will do that calculation for you. So in a TI calculator, you're going to enter vectors one of three ways. The one that is not included in the list I'm giving is the TI Inspire. You enter matrices a little differently in the Inspire, and I'm not exactly sure about the syntax, but if you have trouble doing it, we can figure it out for sure. I've done it before. I just don't remember the syntax. So to enter vectors, there are three ways you can do it. And which ones, some of them have more than one option. Which ones are possible on your calculator just depends on the model you have. But one is, so some of them have a matrix button, and you go to matrix and then go to edit. And then it asks you for the dimensions of the matrix. You fill that out and just sort of enter the and it's matrices, it can be big arrays of numbers, but it works for vectors just as well. So just make it a, 2 by 1 or 3 by 1, and that's like a 2-element vector or a 3-element vector. Okay. You can also enter it on a lot of them as so square bracket to represent a whole matrix, and then square brackets represent each row of a matrix. So you'd enter it as like A, B, C, and that would give you the column vector ABC. And then I think it might only be TI-89s that let you do this, but it saves a couple of keystrokes. Square brackets for the matrix, and then semicolons to go to the next row. So that's a semicolon, not a J. So A, semicolon, B, semicolon, C, and that enters the same, gives you the same vector as in B. And then once you have vectors entered into your calculator like that, you can just use the regular add button and it'll use the rules of vector addition. That's kind of nice. So then just use the regular add button. To multiply a vector by a scalar, and a scalar is just it's just a number. So that's just saying you're multiplying a vector quantity by something that's not a vector. It's just a number. And so let's say that we're multiplying the vector A, B, C times the number D. And what you get there is you just multiply that number D to each of the individual components. So the X component is dA, Y component is dB, Z component is dC. And again, excuse me, in a TI calculator, you can just use the regular multiplication button. So those rules for adding vectors and multiplying vectors by numbers are just built into the calculator. I numbered add two vectors, so let me multiply a vector by a scalar, so that's number 2. And then a lot of times we want to know the length of a vector, like we're given the components and we want to know the magnitude. So number 3, calculate, I'm going to call it magnitude, but that's what people also call the length of a vector. So if you have a vector, I'm going to call it U, and that over arrow says that your variable is a vector. And let's say that the components are A, B, C. Then the magnitude of that vector is represented as absolute value of the vector. And to calculate that, it's the sum of the squares of the components, so A squared plus B squared plus C squared, all square root. And the reasoning of that is just Pythagorean theorem. You can think of, it's easier to visualize in 2D, but it's the same thing in 3D. In 2D, you can imagine the components of a vector and the vector itself make a right triangle. And so the length of that hypotenuse of the right triangle is just the sum of the squares of the legs, square root. Some TI calculators, I don't remember which ones, some have a built-in function called norm. Norm. And so you would enter like norm of, well, let me do one I know. So you'd enter norm of the vector, like, let's say 3 semicolon 4 semicolon 0. And that would give you the length of that vector, which would be 5. And the magnitude of a vector is useful for calculating the next one. So a lot of times, and we'll talk about the applications of this, we'll use this all the time, but a lot of times you want to calculate a unit vector, so a vector with a magnitude of 1 that's in the same direction as a given vector. So calculate a unit vector that's in the same direction as an input vector. I think maybe at the end of class today, we'll get into the first explanations of why this is going to be a really important thing in statics. But basically, like most generally, this is useful in cases where you know a vector variable's direction, but you don't know its magnitude. Okay, so if you come up with, so let me just write that, and this will be a recurring theme. So it's useful when you know a vector's direction, but not its magnitude. I almost put an apostrophe there. Apostrophe there. Okay, so let's say that we have the vector u, and it's equal to a, b, c. Well, we already know that, and what we want is the unit vector in that direction that I'm going to call u with a caret thing on top, different hat. So this is, this notation means it's a unit vector. Okay, so the unit vector in that direction is equal to 1 over the magnitude times the original vector. And so if we wrote that out in components using a, b, and c, that's 1 over the square root of a squared plus b squared plus c squared times the vector a, b, c. And 1 over this magnitude, that's just a number. And so you'd use the rules for multiplying a vector by a scalar to come up with that unit vector. In TI calculators, some TI calculators have a function called unit and then capital V. And that'll do all this for you, so you don't have to enter anything in. And all of these things that I say are built-in functions in some TI calculators. If your calculator doesn't have these functions, it's only a couple lines of code in their programming environment to make these functions. So if you're interested, bring your calculator to office hours, and if it's not already built in, we can just put the programs in there. Oh, like, how long ago? It's probably a long time ago now, but 5 years ago or something, somebody in like statics or deform or something came to me and they're like, can you help me program in all the, I just got this calculator at, it was like Pan America or something. I just got this calculator at Pan America. Can you help me put all these programs in? And I went, and all the programs were already in there from like one of my classes. Like all these were like somebody had gone and pawned it who'd taken my classes. It was funny. Okay, so the way you would enter that if you do have that function built in is unit V and then parentheses and then, something like 4, -6, 12 or whatever. It would give you, well, I don't know what the unit vector in that direction is, but in the vector review that's on D2L, there are examples with numbers and solutions that work out. So you can try it on your calculator and make sure you're doing it right and check the answer at the end. Anybody have any questions about these yet? You need the parentheses. So everything in the parentheses makes that like an argument to that function. I know everybody here has like different background. Like some people haven't taken programming yet and some people have and whatever. But that just means that inside the parentheses is the vector input for that function. Okay. So like if you're just entering that vector, you don't need the parentheses. You just need the parentheses to put that vector into the function. Okay, and now there are two ways to multiply two vectors together. We talked about how to multiply a vector by a scalar. So this is number 5. So this is multiplying two vectors. And there are two ways to do this. Can anyone think of what the two ways to multiply two vectors probably are? Yep, dot and cross. Yep. So there are two ways, and I'm sure there are a million ways that are useful in some applications. In this class, we're going to use dot product and cross product. The first one is, so dot product. And the second one is cross product. And the dot product, when you multiply two vectors together, you get a scalar output. So the result of multiplying two vectors is just a number. And the cross product, when you multiply two vectors, you get another vector out. Okay, so first dot product. So let's say that we are multiplying, so we're taking the dot product between a vector A, B, C and a vector D, E, F. The result of that is going to be A times D plus B times E plus C times F. So notice that's just a number plus a number plus a number, so that output is a scalar. In a TI calculator, so first of all, some of them have a built-in function called lowercase dot and then uppercase p. And so you would do that as like dot p, and you'd put in like the first vector would be 1, 2, 3. So that's the first vector, and then a comma, and then the second vector, let's say 3, 2, 1. And that would give you 1 times 3 plus 2 times 2 plus 3 times 1, so 10. Another way you can do it is you can see if you like this approach. You can use the normal, just the regular multiplication button. If you set the left vector as a row vector, as a, I guess row matrix, and the right vector as a column matrix. I'm getting to that. For dot product, right, the order does not matter. But but you do have to make the row vector be on the left. So it doesn't matter whether you have 1, 2, 3 or 3, 2, 1 on the left, but the left one has to be the row. So you could do this as, like, for example, you could have the vector 1, nope. So for a row vector, you'd actually write this as 1, 2, 3. Because the inner square brackets just switch to the next row. And then you'd multiply this by 3, 2, 1. and that would give you 10. I don't know. If you like that, you can do it. If you don't, it's easy to find something else that works better. There are a couple of important things to keep in mind about the dot product. Notice. By the way, whenever I say notice, that means it's very likely to come up on quizzes later. So pay attention to that when you go back and reread your notes. Okay, so there are 5 things to notice here. The first one is the dot product is often called a scalar product. Why do you think that is? That's right, because the output is a scalar. Second, two vectors that are oriented within 90 degrees of each other so we'd be talking about, like, this and this, for example. If you put them tail to tail, the angle between them is less than 90 degrees. Have a positive dot product. Third, two vectors that are oriented more than 90 degrees apart. The orientation is different by more than 90 degrees, have a negative dot product. So more than 90 degrees apart. So an example of that would be like this dotted with this. So if you put those two tail to tail, that's an angle of more than 90 degrees. Have a negative dot product. Fourth, what do you think the fourth one's going to be? So we have more and less than 90 degrees. Yeah, exactly 90. And what do you think the dot product's going to be? 0. So two perpendicular vectors have a 0 dot product. And then the last one is the question that you just asked a minute ago. What about the order? Order does not matter for dot product. In other words, a vector A dotted with a vector B is equal to B dot A. Any questions about dot product? Okay, so next is cross product. So I don't know, this tree structure is getting a little messy, but this is all under number 5, which is multiplying two vectors. I call dot product 5a. Let me actually change that a on here. And so now cross product, I'm going to call 5b. And if you have so if you're taking the cross product between a vector A, B, C and a vector D, E, F, we know we get a vector out of this, and that vector is going to be, it's going to have an X component of, and so here's how I think about it. So if you write it like this, with the components written out, the X component is going to be cross out the X components. We're not using this for that. And then you go cross minus cross. Okay, so cross goes out, BF minus CE. And then for the Y component, we're going to cross those two out. Cross out the two Y components and cross minus cross. So AF minus CD. And there's one more thing we have to do with the Y component. The Y component always has to be the difficult one. In any kind of vector calculation, it comes up over and over again. Like the Y component always wants to be kind of like part of the team, but it always sort of wants to do its own thing. Like somebody who like wears like fancy socks with their basketball uniform or whatever. Like, why can't you just be like the rest of us? It can't do it. So that is the negative. And then the Z component, cross out the Z components, AE minus BD. On a TI calculator, some have a built-in function called lowercase cross capital P, and it would work like this: cross P, and then in parentheses put your vectors. I'm going to do so 1 0 0, and then the second vector, so comma to separate the two vectors, and then the second vector I'll do 0 1 0. Anyone know what the cross product of the x-axis with the y-axis is? Z-axis, yep. So it'll give you at the vector 0 0 1. If your calculator doesn't have this built-in function, of all the options of all the programs you could enter in your calculator, this is the one you definitely want to enter. It's just going to be a pain in the butt to do this over and over by hand. Okay, so come talk to me and we'll get this entered, and then it'll just be like a one stroke thing to do cross product, because cross product is going to come up in the moment equation of multiple times in every problem we do. Okay. So here are some things to notice about the cross product. The first one is, okay, this is one example of the y-axis always has to be the weird one. Like, I knew somebody who went to, you guys remember the show X-Files? Or you've probably seen it on like cable channels or whatever. Gillian Anderson, I don't know how she pronounces it, but the wife of a friend of mine used to go to high school with her. And she was like, yeah, nobody liked her. And one summer she spent like 2 months in England and came back and talked with a British accent for the rest of her high school career. Like, that's what I'm talking about. She's just like a y-axis, you know? The y-axis always has to be the weird one. Um, Second, the cross product is often called the vector product. Why is that? Yep, right, because the output is a vector. Um, 3, the output vector is perpendicular to each of the 2 input vectors. That happens to be a super useful fact about the cross product. So the output vector is perpendicular to each of the 2 input vectors. Um, 4, the cross product of 2 parallel vectors is 0. Okay, 2 more of these. This is a long list, but number 5, what's known as a right-handed coordinate system I'm going to write coordinate system a lot, so I'm going to abbreviate it CS. Right-handed coordinate system requires that I cross J is equal to K. J, I'm leaving a space here for the weird one. J cross K is equal to I. And then Gillian Anderson axis says I cross K, I didn't leave enough room, is equal to negative J. And then the last thing to keep in mind about cross product is remember that dot product, the order doesn't matter. You can switch it around, just like multiplying numbers. 6 times 4 is 4 times 6. With multiplication, we're used to this idea of mutability. That's not true with the cross product. So order does matter with cross product. And the way it works is A cross B is equal to negative B cross A. Any questions about any of this? Okay, so now that's the end of multiplication of two vectors. So now we're going on to part 6. And that is calculating a vector from A to point B. And you can think of the positions, locations in space, the coordinates of locations in space as being vectors. They're vectors from the origin to that location. So I'm going to represent those as vectors. A lot of times I'll also, instead of saying from A to B, a lot of times I'll say to B from A. So that means the same thing. So don't get fooled by the order switch. And there's 2 ways to do this. So the first one, 6A, is if you know the coordinates of A and B, if you already know the coordinates, A and B, then I guess I'll write it as the vector D, like displacement. Then D is equal to, we're going to B from A, so B, the destination point minus the starting point, is the vector that goes from A to B from A. So that's easy. If you have the coordinates of the two, just do that subtraction, and that gives you a vector that points from one to the other one. If you don't already know the coordinates, then put the origin, or let me change this wording a little bit. So let me just say temporarily. So temporarily, this doesn't have to affect where your origin is for the whole problem or anything. Temporarily put the origin at A, then D is equal to the coordinates of B. Okay. So in all this, B is the destination. And A is the starting point. Okay, so let me do an example of this. Let's say that we have an object, a long beam that's connected to a wall. And let's say that we know that the length of that beam is 0.5 meter. So 0.5 meters. And we know that the angle of this beam with the horizontal is 30 degrees. And let's call this point B and this point A. And we want to know what's a vector 2B from A in the coordinate system that we're used to with X horizontal and Y up. Okay, so this is an example where we don't start the problem already knowing the coordinates of those 2 points. So we're just going to imagine temporarily, we're just going to put the coordinate system at that point A. So this is A. This is B. This angle is 30 degrees. And so with the origin at A, at the starting point, to calculate the coordinates of B, we're just going to go 0.5, that's the length of the beam, times the cosine and sine of 150 degrees. And so that is negative 0.4 433 and positive 0.25. And that's a vector starting at A, going to B. And it sound kind of funny because in a way this seems like such a simple skill compared to a lot of this stuff we're going to do. But I really find the more I think about it this way, the more I notice it. Being good at this kind of stuff in 2D and 3D, because this same way of thinking about it works in 3D too, is the biggest determinant of how you're going to do in this class. Like, it's the most important skill to determine whether this class goes well or badly. So if this stuff is confusing, come talk to me early and we'll try to make sense out of it. And because this just comes up in like every problem for the rest of the class, you know? And if you don't get over this, you can't, it doesn't even, you don't even get to find out whether you know the rest of the stuff, kind of. Okay. Any questions about that? Um, okay, and the last one I want to do is, we already talked about unit vectors if you're given a vector, but I want to talk about just sort of generally unit vectors in a certain direction. So calculate a unit vector. Is this? So calculate a unit vector in a given direction. Okay, so there are two ways to calculate this. The first one is, so 7a is if you're given the angle between a desired vector and some reference, some reference line. This way of doing it, I would only use this in 2D. The second approach we're going to use, you can use in 2D or 3D, but this one is often faster. So a lot of times you'll want to use this one here in 2D, but don't ever mess with it in 3D. There's always a better way to go if you're doing a three-dimensional problem. So an example of this would be like, let's say that you have a wall and a cable connected to the wall, and the cable's connected to an object like this, and we don't care what happens over here. But let's say that we know that this wall makes an angle of, this looks like 50 degrees with the horizontal maybe. And let's say that we know that this angle is, what does that look like, 30 degrees? And let's say we're using a coordinate system like this. Okay, so what we want to know is the orientation of, so let me redraw this coordinate system. and we're trying to figure out a unit vector in. So if we're isolating that ball that the cable's connected to, so it depends what we're looking for here. But let's say we're isolating the ball. Okay, so the cable force on the ball is pulling to the left. Okay, and so we're trying to figure out that direction. Okay, the force pulling that way on the ball. Okay, so how are we going to do this? Well, you might be able to sort of, if you've drawn these angles carefully, then you might be able to figure out that that's just going to be, you know. But there's a systematic way to do this that in confusing cases can be really helpful. And that is, we're going to start like this, and we're going to keep defining vectors that, so we're going to keep defining vectors that where we know the relationship between the coordinate system and that vector. And we're just going to hop from vector to vector given the relative angles that are provided. So the first thing I'm going to do is, I guess I'll do these in blue. This black one is the one we want. So we'll start out with this one, because we know that this angle is 50 degrees. Okay. And so I'm going to start at the positive x-axis, and I'm going to go counterclockwise on the positive x-axis. And so from the positive x-axis to that blue vector, what's the angle? 130, right? Yeah. So theta is equal to 130 degrees. And now we're not given the relationship between this vector and the black vector that we want. What we're given is, well, we could think of it as if we extend this line, and this is SAT math. You probably remember this stuff from geometry. I don't remember what those are called, maybe vertical angles, is that right? But anyways, this angle has to be the same as this. Okay. And so now we can go from 50 so we can go from here to here is an angle of 30 degrees. I guess I just drew my angles really badly. And so now how do you get counterclockwise from that first blue vector to the one that we want? How far do you have to go? But so now you just need to go counterclockwise 30. If you had to go clockwise, you just make it negative. And so now you can go from here, counterclockwise another 30. So we're going to add 30 to our total. And so the total angle you have to go from the positive x-axis is positive 160 degrees. And now the unit vector is just, I'll write it as u with a unit vector hat. And that's equal to cosine of 160, sine of 160. And this way of doing it is which is, I think I can do that. That's negative 0.940, 0.342. And that's really useful, especially in cases where you're given an angle to a wall, from horizontal to a wall, and then an angle from the wall to something else, and then the angle from that something else to the vector that you want. You can just hop around step to step. You know the relationship between this and this, add it to this and this, add it to this and this, and when you finally get to the vector you want, you have the total angle. Anyone have any questions about that? The other type of unit vector we're often going to use, so this is 7b, is instead of knowing the angle between the vector and some reference, we're given 2 points along the vector's path. Okay, so an example of that, this is useful a lot of times when you're dealing with cable tensions. This works in 2D or 3D. So you're in 3D, this is always the way to go. You don't want to deal with angles because, yeah, it just takes crazy three-dimensional thinking to think of like an angle in this plane and then come over here, and you don't want to do that. So this is the approach anytime you're dealing with 3D. And this comes up in cases like, for example, say you have a beam here, and you know that the coordinates of this point are 5, -6, and the coordinates of this point connected to the wall are 7, -5, let's say. And we want to know what's a unit vector. That's in the direction of the force that the cable applies to the beam. Okay, well, the cable applies a force in this direction to the beam. So the way to do that is first calculate a vector that goes from the starting point to the ending point. I'll call that D. So D is just equal to 7, -5, -5, -6. And so that is 2, +1. And now the unit vector in that direction is just equal to 1 over the magnitude times the vector. So that's 1 over 2 squared plus 1 squared square root times 2, 1. And so that's 2 over root 5, 1 over root 5. it doesn't matter at all to me. And actually, I'm so sloppy with that kind of stuff. I usually just put it as a decimal. You know, you can do as much rounding as you want. But the reason this is the way to go in 3D is because it tends to be a lot easier to calculate coordinates of points in 3D than it does to deal with angles in multiple planes. Okay, so come up with the coordinates of the points, do the subtraction, and then take the unit vector in that direction. Anybody have any questions about any of that? Okay, well, that's all I want to say about the vector review. So let's just stop there, and I'll assign some vector review problems for you to sort of solidify this stuff, and then we'll get going with statics on Tuesday. Okay.